Part 2 of 6.2 is on end behavior. And when we talk about end behavior, that is asking what do the graphs do in the ends, thus the name end behavior. Another way to say it is what is happening to the y's. Are the y's rising? So that would be going to positive infinity, or are the y's falling, decreasing, which would mean it would go to negative infinity. So we are going to look at end behaviors. And when we do that, we look at the left of the graph, which means x goes to negative infinity, and the right of the graph, which means x goes to positive infinity. And then we state which of these occur. Does y rise? So does y go to positive infinity, or does y go to negative infinity? So first, let's take a look at the even degree. And it says my coefficient is greater than 0, so that means that is a positive a value. So first, let's graph this even degree. So this is x squared and x to the fourth. The 2 and the 4 are both even. So if I do my little table and put 0 in for x, I get 0, 0, 1, 1, and symmetrically negative 1, 1, 2, 4, and symmetrically negative 2, 4. And I get this parabola. Likewise, if I graph x to the fourth, put 0 in there, I get 0. Put 1 in there, I get 1. Negative 1, I get 1. 2 to the fourth would be 16. Negative 2 to the fourth would be positive 16. So I still get this parabola, just a little sharper. So when we are asked about the end behaviors, first we go to the left, which means as x goes to negative infinity, what happens to my y's? So here is going to the left, x headed towards the negative infinity. What is happening to these y's? These y's, no matter which graph I'm on, are going up. So that means my y's also go up is to positive infinity. Now let's look at the right side of the graph, which is as x goes to positive infinity. So this is the right side of the graph. What is happening to these y's? They go up. So y's go to positive infinity. Okay, let's look at the same degree, even, but let's look at a negative a. So notice I have negative x to the fourth and negative x to the eighth. Both of those are even. So 0, 0, 1, negative 1, and symmetrically 2, negative 16, and negative 2, negative 16. We could go like this. 0, 0, 1, negative 1, symmetrically, and then 2 to the eighth is way off the graph, so it's going to go even faster this way. So when I am looking at the end behaviors again, I'm going to look to the left as x's go towards negative infinity. What is happening to these y's? This one goes down and this one goes down. So that means my y's go to negative infinity. That is down. Then when I look at the right of the graph, that would be as the x's go towards positive infinity. what is happening to these y's? They are going down, so down would be negative infinity. So notice, no matter what, when my degree is even, my end behaviors are the same. Whether my coefficient is negative or my coefficient is positive, my ends are still the same. When my coefficient is positive, my ends are positive. When my coefficient is negative, my ends, my y's are negative. So now let's look at an odd degree. And we'll still look at the leading coefficient being positive on an odd degree. So I have x cubed and x to the fifth. So if I put 0 in there, I get 0. If I put 1 in there, I get 1. If I put negative 1 in there, negative 1 cubed is negative 1. 2 cubed would be 8. Negative 2 cubed would be negative 8. So I get this graph. Do the same for x to the fifth. Put 0 in, I get 0. 1 to the fifth is 1. Negative 1 to the fifth is negative 1. Negative 2 to the fifth is negative 32, so it's way down here. Negative 2 to positive 2 to the fifth is positive 32, so it's way up there. So I get this graph. So now we're going to look at the end behaviors. As my x's go over here to the negative, what is happening to these y's? The y's also go down, so that is to negative infinity. As my x's go to the right, which is towards positive infinity, what is happening to these y's? They go up, so that is towards positive infinity. So notice that my ends are different on an odd degree. But as the x's go negative, the y's went negative. Negative, negative makes that positive a. As the x's go negative, the y's, as the x's go positive, the y's went positive. So positive, positive also makes that positive a, no matter which graph we were on. So just like over here, when I had a positive a, these were my graphs in the even. When I had a negative a, it just flipped my graphs. Do you see that? Flipped them down. So the same thing is going to happen when I have a negative odd degree. On this side, I started in quadrant 3. So this went negative, so now it'll go positive. So this will, for the negative, will flip up to here. And where this went positive, it'll flip down here to quadrant 4. So let's do that. This is a negative a. We still have the odd degree. So I'm going to have a graph like this. Same with this side. It would be like this. So again, we will start as the graph goes left. Left means x goes to negative infinity. What is happening to the ends, the y's? Either graph, they go up, so that's to positive infinity. Then to the right, as the x's go towards the positive end, what is happening to my y's? They both go down. So down is negative infinity. Notice my ends are both different because it was an odd degree. If I take this negative times positive, it gives me the negative a. If I take this positive times negative, it gives me the negative. So all odd degrees with a negative leading coefficient will start in quadrant 2 and end in quadrant 4. All odd degrees with a positive leading coefficient will start in quadrant 3 and end in quadrant 1. So now let's try some functions of our own and say they're end behaviors. So this function is y equals negative x squared plus 1. I see that my degree is even, and I see that my a is negative. So a negative even should look like this, opening downward. So as the x's go left towards negative infinity, these y's go down, so that is towards negative infinity. So I'm going to write that end behavior. As x's go towards negative infinity, y's go towards negative infinity. Then when I go right, as the x's head towards positive infinity, these y's still go down, so down is negative infinity. So as the x's head towards positive infinity, the y's head towards negative infinity. And there is my end behavior. My ends are the same on an even degree. Okay, let's look at the next one. F of x equals x to the 7th minus 3x cubed plus 2x. So my degree is odd. My leading coefficient is a positive a because it's a 1. So odd degrees that are positive. So to get a positive a, as these x's go negative, I'm going to have my y's go negative because negative makes a positive. So I'm going to have to start here and do something like this. And actually, this graph will have more hills and valleys because I have more terms than just an x to the 7th. So as I go left, as my x's go to negative infinity, what are my y's doing? They're going down. So that is to negative infinity. So on this graph, as the x goes left, negative infinity, the y's go down, which is also negative infinity. Now let's go to the right. As the x's go to positive infinity, these y's go up, which is also positive infinity. So I have to also state that side. As the x's go right, which is to positive infinity, the y's go up, which is positive infinity. Are my ends different? Yes, they are. Negative makes the positive. Positive makes the positive. So this is my end behavior. Now let's just look at the graphs of all the different kinds of polynomials. This is according to the degree. If the degree was 0, it is a constant function. It is a horizontal line. If the degree is 1, it is a linear polynomial, and it is a sloped line. If the degree is 2, it is quadratic, and it forms this parabola. So let's look at the end behavior where they start to curve. As my x's go left, which is towards negative infinity, my y's go up, which is towards positive infinity. As my x's go right, which is towards positive infinity, my y's still go up, which is towards positive infinity. That's because my a is positive there. So then let's look at a cubic, which is a degree of 3. Here is the graph of a cubic. So as the x's go left towards negative infinity, my y's go down. That is negative infinity. As the x's go right, that's towards positive infinity, my y's go up, which is also positive infinity. That's again because my a is positive. This would be my end behavior. And then last, I have my 4th degree, which is a quartic. Quartics, if this was y equals x to the 4th, that would be a quartic. Since this has more hills and valleys, more turns, this is a x to the 4th plus bx cubed plus cx squared plus dx plus e. It has more turns, so it will have more terms. So we still, no matter which graph we're on, we can look at the end behaviors. As these x's go negative, no matter which graph we're on, what is happening to these y's? The ends, the y's go up. So as the x's go left, which is towards negative, the y's go up, which is towards positive infinity. Now let's go to the right. As the x's go towards positive infinity, no matter which graph I'm on, what is happening to these y's in the end? They also go up. So that means the y's go towards positive infinity. So now let's actually try to get a graph, and we're going to use our synthetic substitution to get the points, and we should see these end behaviors. If it is an even degree, notice the end behaviors are the same. If it is an odd degree, notice the end behaviors are different. So let's take a look at the one we have. We have an odd degree and a positive a. So that means my graph, as I go negative, my y's should go negative. So I have to be in this quadrant to start. And then I would end in this quadrant so that they're different. So I would have something like this. I should be able to always do a rough sketch of my graph before I start, because of what I know about end behaviors. So let's actually find these points and see if I get a graph similar to this one. So -3 goes in my divisor box. My powers are 3, 2, 1, and 0, so all accounted for. The coefficient of the cubic is 1. The coefficient of the quadratic is 2. The coefficient of the linear is -1. And the coefficient of the constant is 3. Draw my line and bring down my 1. -3 times 1 is -3. Added to that 2 gives me -1. -3 times -1 is +3. Added to this -1 is 2. 2 times -3 is -6. Added to this 3 is -3. So f of -3 is -3. Now we're going to do the same thing, only with -2. So my polynomial was 1, 2, negative 1, 3. Bring down my first term. Negative 2 times 1 is negative 2. Add it to the 2 is 0. 0 times negative 2 is 0. Add it to the negative 1 is negative 1. Negative 2 times negative 1 is 2. Add it to the 3 is 5. So f of negative 2 is 5. Now I'm going to do the negative 1. Negative 1 times 1 is negative 1. Added to the 2 is 1. Negative 1 times 1 is negative 1. Added to the negative 1 is negative 2. Negative 1 times negative 2 is 2. Added to the 3 is 5. F of negative 1 is 5. I'm going to do direct substitution for the 0. So if I put a 0 in here and here and here, I get 3. And then I'll do synthetic on the 1. 1 times 1 is 1. Added to the 2 is 3. 1 times 3 is 3. Added to the negative 1 is 2. 2 times 1 is 2. Added to the 3 is 5. F of 1 is 5. So I'm going to come over here and plot these points. Negative 3, 3. Negative 2, 5. Negative 1, 5. 0, 3. 1, 5. So I started with this one, so I'm going to curve through all my points. Notice here I didn't just go straight, I have to curve through it. Is this graph similar to what I started thinking? Yes, it is. So that does make my end behaviors match according to the degree and the leading coefficient. Now you go ahead and try to graph some and do their end behaviors.